Okay, now let's relax a little bit with this easy next exercise. I'm sorry, I completely overdid it with this problem set, but there are so many nice exercises that I didn't want to leave out, and it's really important stuff, and at some point you have to learn that. All right, so we have a map between sets, and remember that the fiber of an element here under F is defined as follows. F inverse of y. For the umpteenth time, this does not mean that F has an inverse and that this is this inverse applied to y, because then it would simply be one element. But this is the notation for F inverse of the subset consisting of only one element of B. And this can be written down for every map, be it bijective or not. So it doesn't need to have an inverse. This is simply the definition, so we take all x in A that get mapped to y under F. Now, if F is injective, what does this mean? It means this here cannot happen, that two different elements get mapped to the same y. Meaning that in this fiber here, there can't be more than one element. There can't be two elements or more. And of course it could be empty, because it might be that y does not get hit at all. F does not have to be surjective. So this here is injectiveness using the language of fibers. The cardinality of this fiber, meaning the number of elements, can be at most 1. What does surjective mean? It means that every y gets hit by F. So all these fibers must contain at least one element. It's not possible that a fiber is empty, because if this fiber were empty, there would be no x here that gets mapped to y, then y would not be in the image of F, and F would not be surjective. So this here is the condition in fiber language for F to be surjective, and of course bijective means both taken together, and this is the case if and only if all of the fibers, all of them, oh sorry, this means for all, this is a short notation, I think we talked about that. This reflected A for all elements in B, the fibers consist exactly of one element. So every element here has a unique pre-image, and only in this case it is possible to talk about the inverse map from B to A. All right, now wasn't that nice and relaxing? Okay. Okay, exercise number 5, we need to prove the rest of proposition 14. And I thought to myself, well, I'm clever, so I'm not gonna wipe this blackboard clean, but leave proposition 14 on here and then record this part of the solutions first, so I can refer to the proposition 14 on this blackboard. But of course I completely forgot about that and wiped the blackboard clean. So here you see proposition 14. Okay, this here is so easy that it is hard, especially for beginners. I've seen a lot of my students struggle with this kind of stuff. This is completely normal in the beginning. So we need to show, and as I've said before, if you're not sure how to do it, please write down what is it that I need to show. You need to show that this here is a subset of this under this assumption here, that M1 is a subset of M2. And this exactly means that if I have an element of this set, I call it Y because we are in B, then this must also lie here. This is exactly the meaning of being a subset. All right, so we take an element of F of M1. So now what does this mean by the definition of image of a subset? That means exactly that I can find an x in this set, M1, such that y is of the form f of x. Definition of image of a subset. So we haven't used our assumption yet. We know that M1 is a subset of M2. So if x lies in M1, then automatically it also lies in M2. But what does that mean? That means that this here, y equals f of x, is an element of f of M2, because x is an element of M2 as well. And that is it. Now here I forced myself to write it on the blackboard as I would write it in an exercise sheet that I have to hand in. At least in the beginning, please force yourself to do that. Use a lot of words in text and do not simply write down, well, this and that that follows, because later on, if you have to write a thesis or a paper, you need to express your thoughts using whole sentences and a lot of words and not simply formulas. So that's a good habit to get acquainted to this kind of writing right from the beginning. Okay, now this one we do a little shorter, and a lot of times I can't always write so much stuff on the blackboard, so you have to get used to do that yourself if you take notes. So, second statement of part 1, if n1 is a subset of n2, now in the codomain B, then the pre-images also fulfill this condition. So, let's take an x, now I call it x because the pre-image lies in A. X in this pre-image, this means exactly that x gets mapped under F into the set n1. But now, by assumption, n1 is a subset of n2. So that means that f of x also is an element of n2. And this, by definition, means that x is an element of F inverse, the pre-image of n2. Simply the definition of pre-image. Yeah, and this from here to here means exactly that. If I take an element here, it also lies in here. So this is a subset of that. So nothing really happens here, but simply writing down definition after definition. And again, this is hard for a beginner, or this might be hard, so do not despair, you will get used to it. Okay, part 2. First of all, F behaves well with respect to union, meaning exactly that. Doesn't matter if I take the union of two sets first and then map this set, or if I map the sets separately and then take the union in B. Let's prove this. As I've said in the video, for a beginner it's maybe better to do it both ways. First show that this set lies in this set and the other way around, and then they must be equal. I'm doing it the fast way and not in those two ways because otherwise this solution will blow up even more. And it's simply applying definition after definition. So I take an element here, I call it y because we are in the set B. Okay, by definition of the image of a subset, this means y can be written as f of x with x lying in this set here. Definition of image of a subset. Now comes the definition of union. Please write that over these equivalence arrows. Union means x lies in M1 or x lies in M2. This is this or here. Not an exclusive either or, but simply or. But this here exactly means that y is an element of f of M1 or y is an element of f of M2. And this means exactly by the definition of union that y lies in this union, and this is it. Because we have used equivalences, we have seen an element lies here if and only if it lies here, proving the equality of these two sets. Now here with the intersection something can go wrong, and that is that the intersection here might be the empty set, so there is no element in it. Okay, easy example using functions would be that. You can also construct example using these cookie diagrams with 3 dots and construct an example there, but I think this here works well. Take M1, the interval from -1 to 0, 0 excluded, and M2 to be the interval from 0 to 1, 0 excluded. Then clearly the intersection of those here is the empty set. And f of the empty set is defined to be the empty set again, and the empty set is always defined to be a subset. I didn't mention that, but this is elementary set theory. The empty set is considered to be a subset of any set, so even in this case this is true. But of course you do not have equality, because what is f of M1? This is this interval here from 0 to 1, 0 excluded, and this is the same. So this intersection is the interval from 0 to 1, 0 excluded, whereas this here is the empty set, so it's definitely not the same. So this would be a counterexample. Now for the quick proof of this inclusion here, if y is an element of this set, this means y can be written as f of x with x lying in the intersection. But what does it mean to lie in the intersection? It means that x lies in M1 and in M2. If it lies in M1, then y is an element of this. And because it also lies in M2, y is also an element of this, thereby lying in this intersection here. Okay, I'm running out of camera time and space here, so what I just said, y is of this form with x lying in M1 and M2, and this means exactly that. Y lies here and lies here, because it is of this form. So this shows, okay, stop, this is bad. I just convinced myself that we have all these equivalences here, which would mean that here I must have an equal sign, which I just showed to you is not true. And I really had to think about this for some minutes, where my mistake was. It is here. Well, first of all, assume that this intersection here is non-empty, because if it is empty, then by definition, as was hinted in the exercise, f of the empty set is again the empty set. Of course, we do not have any elements that we would map. And the empty set is defined to be a subset of any set. So in the trivial case where this here is the empty set, which I actually used as an example here, this is always true without any need for a proof. But I could have changed this example here with these sets so that the number 0 belongs. Then the intersection of both is not the empty set, but the singleton set consisting of 0. F of 0 is 0, and this again is clearly a subset of the intersection of those two images here, which is simply the interval from 0 to 1. All right, but I digress. So let's assume there is an element here at all. So otherwise we are in the trivial case I just discussed. Now this here is not equivalent. Why? So this here is important. What goes wrong here? This function belonging to this graph is not injective, and then exactly something like this here can happen. If the function is injective, then this here can't happen. So here, going back is not possible in the case of a non-injective map, because then an element here could be an element of this, for example, by mapping, I don't know, this number here, and can belong to this set by being the image of this number here in the other set. And then it is not possible to write it as f of x with a unique x. This is the problem. So this, of course, is true if it can be written in this way with a single element x belonging to both sets, then it is in here as well as in here, so it's in the intersection. But there's no going back if my f is not, in general, there's no going back if f is not injective, as can be seen here. So, all right, so this shows if I start here, if there's an element at all, I only end up here. So this proves this inclusion, and the other inclusion, as we have seen, must not be true. All right. And as a remark about the empty sets, here we don't have the problem. If we assume that M1 and M2 are non-empty sets, then so is their union, and so are these images here. If you want to include the case of empty sets, then it's also true. If, for example, M1 is the empty set, then this union is M2. This here is the empty set union with f of M2, so simply f of M2 equals f of M2. So here we have no problem at all, even with the special case of empty sets. All right. Now this is the correct proof. All right, part 3 of proposition 14. When there is an union, we already proved that in the video for this lesson. Now we have to prove it for the intersection, showing that the pre-image behaves well with unions and with intersections, not like the image. Okay, all right, so that we do not forget this case, with intersections you always have to be careful because they can be empty even if the sets themselves are not empty. So let's look at the case where this intersection here is empty. Then this pre-image, of course, is also the empty set, because if there were an element here, then f of x would have to lie here, which is impossible because this is the empty set. So on this side we have the empty set. So for this to be true, the other side also must be the empty set in this case, but it is. Why? Because assume we have an x that lies here. So there exists an element, so this is not the empty set. This would mean, by definition, x would lie here, so f of x would lie in n1, and because we have the intersection, x would lie here, meaning that f of x would lie in n2. Yeah, but then f of x would be an element of the intersection, n1 intersected with n2, but by assumption this was the empty set. This is a contradiction, so this really needs to be the empty set as well. All right. So we start with an element here, and we may do this because this is not the empty set. Oh no, I'm sorry. This might still be the empty set if simply no elements of A get mapped to this intersection. So I'm sorry. So we have to also check the case where this here is the empty set. This by definition means that no element of x can be mapped in here, because otherwise x would be an element of this set here. So in this case we need to show that this intersection also is empty, and this goes exactly as we did before. All right. So but here the special cases are actually not so trivial. You still have to understand the definitions here. So in the trivial cases, no, in the special cases where empty sets occur, this equality holds. So now finally we may assume there is an element in here, because we're in the case where this is not the empty set. Now comes the definition of pre-image. This means exactly that f of x lies in here. So above this you have to write definition of pre-image. Now by definition of intersection, this means that f of x lies in this set and at the same time in this set. But now again, by definition of pre-image, if f of x is an element of n1, then x lies in the pre-image of n1 under f, and the same here. And now this means exactly that x lies in this intersection because it lies in both sets. And all these equivalences show that this set and this set are always the same. There can be no exceptions here, as in the case with mapping or looking at the images under F. Here we always have equality. All right, and this concludes the proof.